Okay, let's see if we can combine some of our point charge formulas and expressions we've been using together a little bit. So here we have a 4.9 millicoulomb charge, 16 centimeters away. We've got a point in space, doesn't matter where it is. And we are going to find out what is the electric field and what is the electric potential at that location. Now we can't find force, we can't find potential energy because there's nothing there, but we can find those two things. So let's just start with the electric field. The electric field, of course, would be kq over r squared. We've used this expression before. We've got the k, we've got the q, divided by the 16 centimeters, change that to meters, don't forget to square it. And we'd get 1.7 times 10 to the 9 newtons per coulomb. And if you're going away from the charge, it'd be going out this way, so it looks like around maybe something like that. At that location, there we go, all done. Okay. So now let's find the electric potential. Okay, so for electric potential is the voltage. So V is equal to KQ over R. So pretty much the exact same calculation. So we calculate things out and should get 2.8 times 10 to the 8 volts. And it's not a vector, it's a scalar, so there's no direction. It's a positive Q, so just positive voltage, and that's it. Okay, so now let's change this up a little bit. Let's take an electron. Let's put an electron there. So we're going to take this, and I'm going to change that into an electron. Well, now that we have an electron there, we calculate the force and its potential energy. So let's find the force. Now to find the force would be kqq over r squared, so I can do it that way. Or I can just use QE, doesn't make any difference, and I would use that E value right there to calculate the force on that electron. So if I do that, either way, it doesn't make any difference. We will get around 2.7 times 10 to the negative 10 newtons. Okay, now the electron would be attracted to the positive charge, so the electric field is going up right. The force would go down left or so, something like that. Okay, so now let's find the potential energy of the electron. So of course, electrical potential energy is kqq over r, or I can just use qv, and I could take this value and plug it in for my v value right there. So you can do the kqq over r or the qv. It doesn't make any difference how you would calculate it. And when I calculate that one, we should get around 4.5 times 10 to the negative 11 joules of potential energy. And for this one, it's a positive charge and a negative charge. Or if you use that Q here, it'd be a negative charge because it's an electron, and you will end up with a negative potential energy. And yeah, that negative is actually going to be pretty important, and we'll sort of see why in the next question a little bit more. Okay, but there's the basic things. Now I know the thing is, when you're doing this type of stuff, you've got 4 formulas. You've got this one, this one, this one, this one. There's also these two are just combinations. There's a whole bunch of formulas for this type of thing, especially these 4 look very similar to each other. So just be careful, and through practice, you become more consistent with keeping them where they belong, and make sure you still have your little, or you're making your own little formula sheet to keep track of different things. Okay, so let's try another question and combining these ideas together and see what else we can come up with. Okay. Okay, so let's try this one. We've got 2 charges. This is Q1, we'll call this Q2. We got a point in space over here, and over here, let's find out the electric field and the electric potential at that location. Okay, so we'll piece things together and we'll see what we come up with. Now, I'm going to start with the voltage first. And I'll do the first. I got 2 voltages. I've got one from each of the 2 Qs, so I'm going to find those. Actually, I'll color code this differently. Use the green. So I'm going to find the voltage from number 1 would be KQ1 over radius 1. And the voltage for number 2 would be KQ2 over radius 2. and we can solve for each one of those voltages. So for the first one, I should get 4.22 times 10 to the 5 volts. And for this one, I should get 4.88 times 10 to the 5 volts. And Q2 is a negative charge, so this would technically be a negative voltage. All right. So if I want to find out the total voltage at that location, I need to put these two V's together. Now, they are scalar quantities. That's all they are. There's no direction, so I just have to put them together. And this is where making sure you have the negatives kicks in and becomes really important. So I'm going to take those two and I'm going to put them together. But I don't want to add the 4.22 and the 4.88. I want to subtract them because one of them is negative. Or, I mean, I guess you're also adding a negative, whatever. Same mathematically, doesn't make any difference. And I'll put them together. And if I do put them together, my total voltage at the location would be negative 0.66 times 10 to the 5 volts. And that's my electric potential at that location. So again, this is where with my voltages and energies, this is where I always make sure that I include my positives, negatives. Okay, so now let's find the electric field. And we've done this type of thing before, where we take our two electric fields, and that's going to be KQ1 over radius 1 squared. And electric field number 2 is going to be KQ2 over radius 2 squared. And we can find our two electric fields and then put them together. So for E1, we should get 2.41 times 10 to the 8 newtons per coulomb. And that field will be going towards the right. And then E2 should be like 4.07 times 10 to the 8 newtons per coulomb, and that field to be going down. Now we've done this type of thing before, so this is where we have to make our triangle. So if we make the triangle, we've got 2.41 going to the right, we've got 4.07 going down, and we would have our total electric field, something like this. So we'll crack out the Pythagoras and then the trig to figure out the length of the hypotenuse and the angle. All right, there it pops up. There we go. So just solving these Pythagoras and trig, our overall triangle here was 4.73. So it's 4.73 to the 8 newtons per coulomb, bring the power of 10 back, and then it'd be at negative 59 degrees, and that would be my electric field at that location. Okay, so there is the difference between finding electric potential and electric fields from a couple of charges. The potential is easy, like it's because you just have to watch positives and negatives, but there's no angles, there's no trig, there's no Pythagoras, no nothing. You just got to add or subtract them, you just got to put them together. For electric fields, that one's a little more annoying because they are vector quantities, and you have to treat them as such and do angles if you need to. Okay, but now what we can do is let's build on this. Let's put a little charge there. Okay, so let's put a little 0.75 nanocoulomb charge there. Okay, right there. And now that we put a charge there, we can calculate its potential energy. We can calculate the force on it. Okay, so if I wanted to calculate the potential energy of it, I could do the KQ of R's, but I have the total voltage already. So I can just do the shortcut version. I can just do the Q times the V. Now just be careful because that total V was negative. So when you put that in there and you multiply that by the 0.75 nano, your potential energy is going to be negative. And yes, that does matter. And yes, that is important. And we should get 4.95 times 10 to the negative 5 joules. So that is the potential energy of the charge at that location. Okay, now we can do something similar. We can find let's find the force on it. So what would the force be? And of course, the force is just Q times E. You have the E value, the total electric field right there. We have the 4.73 to the power of 8, and we just have to multiply that by the 0.75 to the negative 9 coulombs, because that's the charge that we introduced. and we will get a force of approximately 0.35 newtons. And it would be going, it's a positive charge, so it'll go with the field, so it would be at negative 59 degrees. Okay, so that's sort of the four main quantities you guys would calculate with point charges: potential, electric fields, forces, and EP and all that kind of stuff, and how the sort of things sort of link together. And again, what you could also do is you could also move that charge. I mean, if you move the charge from one place to the other, you may want to find the force to move it. And again, you'd want to use energies for that type of thing because of the chaining radii that would probably be involved. But that's how you could do something like that. Okay.